Hello everyone. Today we'll be starting with Module 3, Flip-flops and its applications. I'm Pavitra GS, Assistant Professor, Department of ECE, Sai Vidya Institute of Technology. In today's session, we will learn what are sequential circuits, what are latches. In that we will learn the operation of SR latch. In this module, we will study about flip-flops and its application. So we will cover the topics such as basic bistable elements, latches, the master-slave flip-flops, under that pulse-triggered flip-flops, SR flip-flops, JK flip-flops, characteristic equation of all the flip-flops, and applications of the flip-flops such as registers, binary ripple counter, and synchronous binary counters. By the end of this module, a student will be able to gain knowledge on flip-flops and its sequential circuits. In the previous sessions, we have learned about the combinational circuit and the design of combinational circuit. Just to revise, we will just describe the combinational logic circuit, then we will try to understand what are sequential circuit. The combinational logic circuits in which the output of the circuit depends mainly on the applied inputs. So if you are changing the applied input, then obviously the output changes instantly. So in sequential circuit, the output of a network, that is nothing but a digital circuit, mainly depends on both present input, that is applied input, as well as the past history, that is memory elements. So such circuits are termed as the sequential circuits. The examples of sequential circuits are latches, flip-flops, registers, counters, etc. So let us see the block diagram of sequential network. So we can observe here that we have a combinational circuit and to which the applied inputs are given, and we have outputs here. We have a feedback path which is given back to the combinational network again through the memory elements. So the memory elements here can be the latches, flip-flops, which are used to store the digital data. So here the output mainly depends on applied input as well as the memory elements. So such circuits are termed as sequential. There are two types of sequential circuit. First one is synchronous sequential circuit and second one is asynchronous sequential circuit. In asynchronous sequential circuit, the master clock signal will not be present. That is, the entire operation of the sequential network will depend only on the applied input as well as the memory elements. That's all. So it is not mainly controlled by the clock input. Whereas in synchronous sequential circuit, we can see that the entire operation of the sequential network will be controlled by the master clock itself. So such circuits are termed as synchronous sequential network. Let us now understand what are latches. Latches are class of flip-flops which is capable of storing either 0 or 1, that is single bit of binary data. It responds immediately to the applied inputs when enabled. These are level sensitive circuits. So latches are always level sensitive circuits. The latches consist of two output lines. One is the normal output, we consider or represent that by notation Q, and complementary output Q bar. If the output of latch is logic 1, then it is said to be in set state. If the output of latch is logic 0, then the latch is said to be in reset state. So we can have two states of storage, that is set state and reset state. Let us analyze the first type of latch, that is RS latch. We can also call it as SR latch. R stands for reset and S stands for set. So let us see the construction of RS latch. It is constructed by cross coupling of two NOR gates as shown in the figure here. As we have two input lines, we can analyze the operation of RS latch by considering four different cases with the RS equal to 0, 0, RS equal to 0, 1, RS equal to 1, 0 and RS equal to 1, 1. Before we start analyzing for each of the case, let us assume the previous state of the latch to be as Q equal to 0 and Q bar equal to 1. Now after assumption of the previous state, let us start applying the input r equal to 0 and s equal to 0. So considering the first NOR gate, we will take back the feedback from Q bar, and the input of one of the input of first NOR gate will be 1. So 0 or 1 is 1, complementary is 0. So the new state is 0 at Q. The same thing is given back to one of the input of the second NOR gate. So 0 or 0 is 0, complementary is 1. So if we observe the previous state here, Q was 0 and Q bar was 1, and after applying R equal to 0, S equal to 0, we are retaining back the same state. So it is same for if we assume the previous state to be as Q equal to 1 and Q bar equal to 0. After application of R equal to 0 and S equal to 0, it remains in its same state. So the same thing applies to the other combination also. We have analyzed for Q equal to 0 and Q bar equal to 1 here with inputs R equal to 0 and S equal to 0. So the final conclusion is when both the inputs are 0, the output does not change, it remains in its previous state itself. So now let us analyze the second state or second case, that is assumption of previous state Q equal to 1 and Q bar equal to 0. Let us apply the inputs as R equal to 1 and S equal to 0. Here we can observe that we have enabled the R input, that is reset input, and we have disabled the set input. So obviously when you are enabling the reset input, expected output should be 0. So let us analyze the operation here. The output Q bar is given back to R equal one of the input of the first NOR gate. So 1 or 0 is 1, complementary will be 0, that is given back to the input, one of the input of the second NOR gate. So 0 or 0 is 0, complementary is 1. Now in this we can observe that by application of R equal to 1 and S equal to 0, the new state of Q is 0, that is reset state. So such condition we call it as reset state. Let us now analyze the third case considering R equal to 0 and S equal to 1. So before we start the analysis, let us assume the previous state to be as Q equal to 0 and Q bar equal to 1. After assuming the previous state, let us apply the inputs R is 0 and S equal to 1. Now the output of Q is 0, which is given as the input for the second NOR gate. So 0 or 1 is 1, complementary will be 0. The new state of Q bar is 0, which is given back again to the input of the first NOR gate. 0 or 0 is 0, complementary is 1. So we can observe that the new state is 1 here. That is, the latch is now in set state. Previously it was in 0 state. As we have enabled set input and disabled reset input, the new state is logic 1, that is set state. The last condition is what happens when both the inputs have enabled. So let us start analysis for the last condition, that is R equal to 1 and S equal to 1. So before we start, we have to assume the previous state. We have assumed the previous state to be as Q equal to 0 and Q bar equal to 1. Let us apply the inputs R equal to 1 and S equal to 1. So Q bar output is given back to the input of the first NOR gate. So 1 or 1 is 1, complementary is 0. The 0 is given back to the input of the second NOR gate. 0 or 1 is 1, complementary is 0. Okay, so now here we can observe that both the outputs are 0, that is normal output as well as the complementary output both are 0, which is not at all possible because the outputs are not complementary with each other here. So this condition is invalid and we call this as a forbidden state. So we have analyzed all the 4 different cases for RS latch. The first case, when R is 0, S is 0, we get previous state, output does not change. For second condition, when reset input is enabled, output goes to 0, whatever might be the state, it goes to 0 state. So this is reset state. When set input is enabled, output goes to logic 1, that is set state. When both the inputs are enabled, the outputs are not complementary with each other, therefore this state is called as forbidden state. Let us see the truth table of SR latch. Whatever we have analyzed in the previous slide, the same thing is represented in terms of truth table, or we can call this as a function table. So we have two inputs for RS latch. So we have represented both the inputs here, and the outputs Q bar is represented by notation Q plus and Q bar plus. The notation Q plus and Q bar plus represents the output after application of the applied inputs. So we represent it as Q plus and Q bar plus. Q bar will be considered to be as a previous state. So for four different combinations as we have analyzed, we have represented the same thing in the function table. So when both the inputs are disabled, output the latch output does not change its state, it remains in its previous state. When reset input is enabled, output will be pulled to 0. So this state is called as reset state. When set input is enabled, output will be pulled to logic 1. So this state is called as set state. When both the inputs are enabled, output remains in 0 0, which are not complementary with each other, so which is invalid, and this condition is called as forbidden state. The figure here represents the symbol of SR latch. So it represents two inputs and two outputs, which are given by Q bar. Now let us see the timing diagram of SR latch. So the inputs are two inputs S and R. We have two outputs Q plus and Q bar plus. So let us plot timing diagram here. Let us draw the timing diagram. So we can consider any random timing sequence. So let me consider one of the timing sequence here. I'll consider this input to be as S and the R input as R input is as shown here. So let us draw the dotted line for every transition of S and R here, so that we can plot Q bar. So the dotted lines are extended. Okay. Now by looking at the function table of SR latch, we can draw the output waveform Q bar here. So let us first plot for Q. Let us assume the previous state of Q to be as 0 here. So let me start for every timing instant. So first timing instant, we have S as 0 and R as 0. So when S is 0, R is 0, Q will retain its previous state, that is nothing but 0. The next timing instant, S is 1, R is 0. So set the input is enabled, so it goes to 1 state. The next duration, small timing duration, both the inputs S and R are 0. So it remains in its previous state. The previous state here is 1, therefore it retains previous state. The next timing instant, the inputs are S is 0 and R is 1. That means you have enabled reset input, so it goes to 0 state. At the next timing instant, S is 1, R is 0. So we have enabled set input, it goes to logic 1. The next timing instant, S is 0, R is 0, it retains in its previous state. The next timing instant, S is 1, R is 0. That is, we have enabled set input, therefore it retains 1 state. The next timing instant, S is 0, R is 0, it retains its previous state, that is 1. So it retains state logic 1. The next instant, S is 1, R is 0, again you have set state. The next timing instant, S is 1, R is 1, where we have forbidden state, so it goes to 0. So while writing the complementary, until forbidden state, it remains the complementary of Q. So I am just writing the complementary waveform following Q output. Now here the forbidden state at the last timing instant is this. So here we have a forbidden state where output remains in 0 itself. So here we have to write 0 state representing forbidden state. So this is the timing diagram for SR latch.